Now that we've reviewed how we do route summarization, let's take a look now at how routers choose which route to use for a specific destination IP address of a packet. Here I have a small network with 5 routers. One is out on the internet there in the cloud, router I, and then we have routers A, B, C, and D here. We're really just going to take a look at router A and router B's routing table to find out how a message is going to get routed using these tables. I've set this up so that there is always going to be more than one matching route for our destination IP address. So here let's imagine that we have a message coming back from the internet with a destination IP address of 10.0.3.10. So that message gets forwarded into our network to router B. Router B is then going to do a route table lookup. So what it'll do is it's going to take that 10.0.3.10 destination IP address in the packet header, and it's going to compare it to each line in our routing table. So we look at the first network here, it's directly connected, and it has an address of 192.168.96.0, which does not match. Our second line here is a static route. This is our static default route, which means all addresses. So 10.0.3.10 is an IP address which matches all IP addresses. So this is a potential route we could use to forward our message. Additionally, 10.0.0.0/22 represents a range of addresses from 10.0.0.0 through 10.0.3.255. And that also is a valid route that matches our destination IP address. And then the last route here, 10.0.3.0/24, also is a route that matches our destination IP address. 10.0.3.10 is in the range of 10.0.3.0/24. So here we have 3 separate routing statements on router B, and all 3 routing statements are ranges of addresses that match our destination IP address. Well, which one do we use then? The rule here is that the router is going to choose the route with the largest number of matching network bits. So effectively here, we're going to choose the route with the longest subnet mask that also matches our destination IP address. In this case, the matching route is going to be the last route there, 10.0.3.0, because it has a 24-bit mask, which is longer than the 22-bit mask for the previous route, and longer than the /0 mask for our default route. So we're always going to choose the route with the longest mask here to forward our message, which is the appropriate route in this case because network 10.0.3.0/24 is directly connected to router D. Let's look at another example. So let's say this time we're destined for IP address 10.0.1.10. So that message is going to come in to router B. We're going to look at the routing table again and compare each line of the routing table to our destination IP address. We don't have a match on that first line. Of course, we have a match on the second line. That is our default route. We have a match on the third line because 10.0.1.10 is within the range of 10.0.0.0/22. And that last line, we do not have a match. 10.0.3.0 does not match our destination IP address. So this time we only have 2 matching routes. Well, once again, we're going to choose the route with the longest mask. So we're going to choose the route with the next hop of router A. We're going to forward that message on. Now we're going to compare our destination IP address to the routing table of router A. And if we look through all of that, we're going to have 2 matching routes once again. The first route is our default route, which has a next hop of router B. And then we also have a static route with the next hop of router C going to network 10.0.1.0/24. We're going to choose that last route because it has the largest number of matching bits in the network portion. So we forward our message down to router C and it's at our destination. 10.0.1.0 is directly connected to router C. Let's do one more example here. This time we have a destination IP address of 10.0.0.10. So message comes into router B. We of course do our lookup here. We're going to see that we have 2 matching routes. We're going to choose the route that has the largest number of matching bits, which is the static route with the /22 mask. We're going to forward our message on to router A. Once it gets to router A, now we're going to do a lookup in the routing table. And now here in our routing table, we once again have 2 matching routes. The first route that it matches, 10.0.0.0/24, is directly connected to router A. Additionally, we have a static default route with the next hop of router B. Well, in this case, since we are comparing a directly connected route to a static route, the router is always going to choose a directly connected route for the destination over a static route. So two things are happening here. One, we are actually choosing the route with the longest matching network portion bits, which is that top address. Additionally, the router really isn't even going to consider that static default route here because it has a match of a directly connected network. So we'll just forward that message right out to network 10.0.0.0. When we look at how routers choose which routes to use then, what we're looking at is if more than one route exists with identical administrative distances, we're going to choose the route with the longest mask to forward our packet. So whichever route has the most number of matching bits with the IP address, that is the route we are going to choose. Well, now that we've looked at how the router chooses which route to use to route packets to their destination, we should also examine how routers choose which route to add to the routing table. So the route that the router adds to the routing table is a completely separate process from what the router does when a packet arrives on an interface and it has to find out what exit interface to send that message out. Adding routes to the routing table, we're going to do this. If our router learns about the same destination network through multiple methods, we're going to add the route to the routing table that has the lowest administrative distance. So let's say that we learned about network 10.0.0.0/24 through EIGRP and through OSPF. We can easily have two routing protocols running on our routers. So the routes that we're going to add are going to be the routes for EIGRP because EIGRP has an administrative distance of 90. Now, if within EIGRP, we learn about more than one route to the same destination, maybe 10.0.0.0/24 is accessible via two paths through the network. If that's the case, the router then will add the route to the routing table with the lowest cost. It's going to add the route that has the best metric to get to the destination to the routing table. Now, sometimes we're going to receive routes that have equal costs to the destination, meaning that the metric is identical whether we take one path to the destination or a different path to the destination. When that happens, typically we're going to add both routes to the routing table and load balance between them. So we'll add all the routes with equal cost paths and then load balance between those two paths when we receive a packet to that destination network. So this is how we add routes to the routing table so that we can then use those routes to route to our destination networks.